Hello, and congratulations. You made it through another chapter. Now we're going to review everything with some standardized test questions. Should be just like what you'll see on your state exam. This one we have circle L, and they tell us that these two chords are congruent. And they want to know which of these statements is not necessarily true. MN is congruent to PQ. Well, in the same circle, or in congruent circles, congruent chords subtend the same arc. So the measure of this arc would have to be the same as the measure of this arc, because the chords that subtend those arcs are congruent. Okay, so this one's true. Now what about this? NQP. Well, that would be this one here. QNM. Well, that would be this one here. Well, from our arc addition postulate, this first one is just NQ plus QP. Well, NQ is, well, let's write down what the other one is first, just to make it totally obvious. And this one here and the other arc, to draw our arc addition postulate, we can write as MN plus NQ. Well, we already know that MN is congruent to PQ, and NQ is congruent to itself. So it's pretty easy to see that these two are congruent. And if you want to lay it out perfectly, you can rewrite this in terms of measures, because you have the measure of arc NQ plus, I can write the measure of NQ plus the measure of QP is equal to the measure of MN. Yes, plus the measure of NQ. Now, NQ is certainly equal to itself, so I could subtract that from each side, or I could just leave it and make a substitution. Either way, it's pretty easy to prove that these two are equal, and that stems from the fact that NQ is equal to itself, and we already know that arc QP is congruent to arc MN, so they have the same measure, so these two are equal. And if they have the same measure, then they're congruent, so that brings us back to this final statement. So this is good too. What about this one? MP and NQ. Well, that's this arc here and this arc here. That doesn't seem so good to me. But let's check the next one, just in case. I think maybe this one isn't correct. MPQ. Well, let's see here. MPQ. And let's see. Well, I drew those two arcs in, and, well, if you can call what I just did drawing. Anyway, I've sort of indicated what these two arcs are. MPQ, that's this one here, and then MNP. And once again, MNP is just this arc plus this one over here. QPM is this arc plus this one over here, and we get exactly the same thing that we got for B. MP is congruent to itself. This one's congruent to this one. So this whole thing has to be congruent to this whole thing. We do it exactly the way we did this thing here. So this is true. That leaves us with this. And it's kind of easy to see why this doesn't have to be true. The way they drew it, it kind of looks like it is, but let's do it this way. Now we've got a circle here. They happen to have drawn these two congruent chords so that both endpoints look like they're an equal distance apart, which would make these two arcs congruent. But it only looks that way. We can't just go by how things look. For instance, I could draw two other. Well, suppose I started with the first one. Say that's MN. But I can draw another congruent arc from, say, here to here. I don't know if those look congruent, but let's pretend that they are. The point is, this arc is definitely not congruent to this arc, is it? They're not even close. You can eyeball that and see that this definitely does not have to be true. It could be, if you lay it out correctly. We could make this, well, let's just say it could happen. But it doesn't have to. And there's absolutely nothing in the given information to indicate that this would be true, because there's nothing in the given information that would prevent us from drawing this. Two congruent arcs. Maybe I should have labeled it. This would be Q and this would be P in this example. So this definitely does not have to be true. Now for this problem, we have to remember our chord segment theorem. Do we? No, actually we don't, do we? We already know this is a diameter and this is perpendicular. So all we have to remember is what happens when the diameter intersects the chord. Well, when it intersects perpendicularly. We could draw other diameters this way that would still intersect the chord, but when the diameter is perpendicular to the chord, it bisects the chord. That's the important part. Which means that PV equals RV. We could write that out. Well, PV is 5x plus 2. Pardon me. As I say, PV is 5x minus 2. Well, PR, that's the whole thing. And if this is bisected so that these are each equal in 1/2 of the whole, then the whole must be 2 times 1/2. Or maybe I should just write that out. For this situation, since things have been bisected, I can write that 2 times PV equals the whole thing, PR. Which means, since this is 5x minus 2 is PV, I can multiply it by 2 and set it equal to the whole thing, which is 4x plus 14. And if we work this out, we get so if we lay this out, do a little expand it, do a little rearranging, subtract 4x from each side, add 4 to each side, and we get that 6x equals 18 or x equals 3. And that, of course, would be B. So all you really had to remember for this one was the fact that when a diameter is perpendicular to a chord, it bisects that chord. And the converse is also true, don't forget that. When the diameter bisects the chord, it is perpendicular to it. It goes both ways. Well, gee, if you get a few more questions like this on your state exam, you'll just fly right through it. Remember, by now you should be able to spot equation of a circle, especially when it's in a nice simple form like this. In the full-blown expanded algebraic form, it might not be so obvious. But when it's written like this, it should take you about half a second to recognize that the center of this circle, the x-coordinate is -2, and the y-coordinate is 4. Remember to keep your signs straight on this. If it's x minus 2, then the x-coordinate is 2. If it's x plus 2, then the x-coordinate is -2. So -2, 4, and it looks like this is the answer here. Really nothing to it. It's hardly even mathematics when you do something like that. It's like just looking it up in a table, except that the table is in your head, and you can instantly spot this is the equation of a circle, and the constants in here tell you what the center has to be. Now with this, this image right here, this is just an exploded view of this, in case we need to make some markings on it and write on it. Less crowded here. Well, if we forget this line, these two chords should look familiar. These are two intersecting chords. We have a theorem involving the segments that these chords are broken up into, but that's not the important part right now. That theorem we have, remember, came from the fact that when we do this, we produce similar triangles, which means that we can't really say too much about the lengths, because with similar triangles, we have to know one of the lengths to figure out the other, right? They're in a ratio. They're not congruent. They're in a ratio. But the angles stay the same. So the angles in this triangle have to be the same as the angles in this one. Now what we want to know, I think, is, QR. That's this one here. So this is the arc we want. This is the angle that subtends this arc, RSQ. If we know this angle, we know from our theorem that the measure of this arc, well, it's just a definition, that the measure of this arc is equal to the central angle, the angle taken from the center of the circle. The measure of this arc is double the inscribed angle here. Or you could say this inscribed angle is half the measure of the arc that it intercepts. Well, if these triangles are similar and have the same angles, we already know this is 105. This is the angle we want to find, because if we find this, then we'll double that and we'll know what the measure of the arc is. 27, well, that goes with this one here. So I guess I could just write it like that. That's 27 and that's 105. So this is 27 degrees and this is 105. We add them up and get 132. The angles in the triangle have to add up to 180. So if we subtract 132 from 180, that'll tell us what this angle is. And this angle turns out to be 48. And this is half the measure of this arc, which means the arc must be, what, 96? 2 times 48? And that would be D. So again, this was fairly easy. You just had to remember that your inscribed angle is half the measure of the arc that it intercepts. And don't forget that all the angles in a triangle add up to 180. When the chords intersect, they produce two similar triangles. Remember those three facts, and this problem's real easy. Well, here we have another one that's not really too tough if you stop to think about it. You almost don't even really need to remember your theorems and things. Just remember one simple fact. it's 360 degrees all the way around the circle. So when we draw our central angle, and let's say that let's say this is K and this is L. We don't need to draw them all in. If they get 6 points here, there will be 6 points all the way around. They're all the same because they tell us it's a regular hexagon. And then we've got this here. Now, what angle is this? Well, if we break it up, there are 6 of these. They're all congruent. And we know that because that's a regular hexagon. So each of these is equal, which means the arcs which they subtend are all congruent. Hence, we just divide 360 by 6 and get 60. That's this one here. There are other ways. You could have remembered some theorems and other things, but I think it's easiest to just draw yourself a picture and just always remember what's going on. That way you can look at things in a very simple way that doesn't require remembering a lot of complicated theorems. Like in this case, you pretty much needed to remember there's 360 degrees in a circle, and that the measure of the arc is exactly the same as the measure of the central angle that intercepts that arc. And then boom, you're done, because figuring out this angle is really easy. Well, with this one, we should remember from previous problems that the diagonals of a kite, that's what this is. Remember, the adjacent sides are congruent. So we have these two sides are congruent, and this side are congruent. And that means this is a kite, and the diagonals are perpendicular. And when we inscribe a kite into a circle, the long diagonal is in fact a diameter. We know that from previous problems, or maybe from the fact that this is a chord. Well, there are other chords that could be perpendicular to it, but it's also true that this long one bisects this, and it's perpendicular, so it has to be a diameter. But the important thing to remember, I think, for a kite is that when you inscribe a kite in a circle, the long diagonal has to be a diameter. And it's also true that for any kite, the diagonals are perpendicular. Now there's another theorem which says if one side of an inscribed triangle is the diameter, the triangle has to be a right angle. I drew in the important lines. Here's the long diagonal, which is the diameter. We have an inscribed angle, an inscribed triangle, in which one side is the diameter. That means that the diameter has to be the hypotenuse of a right triangle. That's from a previous theorem, which goes both ways. If we draw our diameter, draw any point on the circle and connect them up, thereby producing a triangle, it will always be a right triangle. Conversely, if we inscribe a right triangle into a circle, the hypotenuse will always be the diameter of the circle. So, now we're practically done, because we've got TU equals 12, and UV equals 18, so the hypotenuse would be 12 squared. The square of the hypotenuse would be that. And let's see, that's 144 plus 324. Oops. Better grab a calculator, because I'm going to need the square root of that, aren't I? That's going to be the diameter squared. So if we do that, just lay out Pythagoras' theorem, we get 144 and 324 is d squared. D squared is 468. Take the square root of this and get 21.6. I'm not sure what they meant by approximate. That's approximately, I guess you could write 22. Okay, the actual answer was like 21.633333, like that. I just rounded to 21.6. The important part here was recognizing that if the diameter is one part of a triangle inscribed in a circle, then you automatically have a right triangle. And since you've got the two legs of the right triangle, you actually have a very easy way to get the length of your diameter. And here's one where we just use our inscribed angle. Since this is tangent, the intercepted arc is RT. And this is an inscribed angle, so it must be true that 62 degrees equals 1/2 of, say, the measure of the arc, RT. So, we can easily write that RT equals 124. That's this arc here. Why would we want to know that? Well, they're asking you about the other arc. You can call this the minor arc, and this is the major arc. Well, they add up to 360. They have to. So they cover the whole thing. Here, R to T goes to here, and then TR comes right back around to the starting point. So the two together are 360 degrees. If this one is 124, we just have to make our subtraction. And let's see, we get 236, and that's the answer right down here. This was pretty easy. You just had to, again, remember your inscribed angle theorem. And, of course, remember that there are 360 degrees in a circle. Now here we have two circles which they say intersect. What's the maximum number of common tangents we can have? For instance, I've got two circles here which don't intersect. But let's make them intersect and see what happens here. There we go. Thank you. They can intersect like this, in which case two common tangents would be the most we could get, right? We'd have one that went across here and one that was like this, I guess. But there's another way that these can intersect. They can intersect at exactly one point, meaning they're tangent to each other. Now, what we can do is we can draw a tangent line straight between the two circles, which is tangent to both of them. Another tangent line here, and a tangent line here. And that's the most we can do. If this circle moves over, we've only got two tangent lines. If it moves over here, sure, we could produce four tangent lines. We could come right in between the two here, draw another one down here like this, and then a couple across, more or less horizontally. But that only works if they don't touch each other, if they're not intersecting, if we've got space in between the two circles. But they intersect, so they're either like that, or they're on top of each other, like that. Well, they're not the same size, so there's lots of ways they could intersect. But to get the maximum number of tangents, one point of intersection, in other words, where the two circles are actually tangent, that gives you your maximum number of common tangents. I think you can see that pretty easy. Well, again, they're giving us the measures of some Are they overlapping arcs, maybe? I'll have to take a look and see what we've got here. I went ahead and drew in the labeled, rather, the unknown. And it always seems like a pain in the neck to have to write things like M, arc, EF, and MR. I'd rather just assign a variable to it and work the whole thing that way. So EF is beta, GH is alpha. Now what we should probably do is just start writing down what we know and see if that leads to anything useful. EFG, that's this one from E here to G. So that's beta plus X, and they tell us that that's 146. Okay, so we got that. What about FGH? Well, it overlaps, doesn't it? You got F, G, and then H here. So the measure would be the measure of this plus this, just like up here. And that's alpha plus X equals 172. Now this won't get us much, because right now we've got 1, 2, 3 variables, 3 things we don't know, and 2 equations. That's no good. Is there another equation we can throw in here? Yeah, I think maybe there is. The entire thing, all the way around, has to equal 360, doesn't it? So suppose I went EGE. Well, that would be beta plus X plus alpha plus 3X, and that would be 360. So we got beta plus alpha plus X plus 3X, that's 4X. And that's 360. Well, now we've added an equation without adding any unknowns. We've got 3 equations and 3 unknowns. Now this we can do. How about if we figure out beta and alpha in terms of X? We can substitute them into this equation, and we'll have one equation with only one variable, and that will be X, which is good because that's the one we're looking for. So this would imply that beta equals 146 minus X. And over here, this says that alpha equals 172 minus X. So we put that down here. So if we make our substitutions, 146 minus X for beta, 172 minus X for alpha, and then of course X plus 3X, that's just 4X. Now we just have to rearrange everything. We got minus X plus 4X. That'll leave us with 2X. We've got 146 and 172. That's 318. So we subtract 318 from each side and get that 2X equals 42. Or X equals 21. Once again, the trick to this wasn't really remembering that arcs, the additive arc postulate, that's probably second nature to you. EG is EF plus FG. I don't think you have any trouble at all remembering that. Remembering that the circle is 360 degrees. That shouldn't be hard either. What you have to do is not get intimidated when you realize that you've got too many variables floating around. Start looking for equations that you can write down, and if you can end up with as many equations as you have variables, then you've got it made. then you just solve for the other variables in terms of the one you're looking for. Make your substitution and solve for the one variable that you actually want. Okay, here's another one. It's really pretty easy. All you have to remember is that when you draw two tangents from a point outside the circle, which is probably the only way you could do it, the distance from that point to the point of tangency is the same for both tangents. In other words, KL has to equal ML. Or, algebraically, we can write x minus 1 equals 1/2 x plus 5. Now let's see if we add 1 to each side and subtract 1/2 x from each side. I guess we get x over 2 equals 6. And that should leave us with x equals 12. Does that make sense? Well, let's see, 12 minus 1 is 11. On the other hand, 1/2 of 12 is 6 plus 5 is 11. So, I can safely say I didn't make any stupid arithmetic mistakes in this one. Well, to do this one, number one, we just recognize H is definitely the center of the circle. That's why it says circle H. We have a couple of pairs of vertical angles. And the arc, remember, is measured according to the vertical angle. If the arc which subtends this angle, HD, is 111, then this angle itself is 111. And this angle is 111. We don't know what these two are, but they're congruent. And I think they asked for this one. It really doesn't matter, because if they asked for this one, it would be the same answer. The two of these add up to 222 degrees. So, if we subtract that from 360, that's how much we have left over to distribute amongst these two angles, and we have to distribute it equally because they're both congruent. So we do our subtraction and get that we have 138 degrees, but that's the sum of these two angles, which are congruent. So if we take this number and divide it by 2, and let's see, that's 6, 18 divided by 2 is 9, so we get 6, 9. And that would be the answer either way, if they had asked for arc DC or arc AB. This one, all you had to remember was your old vertical angles theorem. And don't forget, there are 360 degrees in a circle. Once you've got that, it's pretty easy. Well, of course you had to remember that the measure of the arc is exactly the same as the measure of the central angle. Now for this one, we need to remember our tangent secant segments theorem. Maybe it's segment tangent secant tangent segments. Some permutation of those three words. It's the one that says the tangent, from the point outside the circle to the point of tangency, the length of that segment squared is equal to the length, the length of this segment squared is equal to the product of the length of this segment times the whole segment. For chords, it's different. If it was all inside the circle, it's one segment times the other segment. When they're outside the circle, it's the outer segment times the whole thing. Well, this squared is 400. And what's this? It's going to be 2x 2x plus 6x, that's 8x. We get 16x squared. Well, if you check your calculator, 400 divided by 16 will give you 25. And that's x squared. So, x equals 5. And that seems to work, because if x is 5, then this would be 10. This would be 30. So the whole thing here is 40. You get 10 times the whole would be 10 times 40. And that is, in fact, 400. So we've got it. Well, they ask us to show that triangle PSR is similar to TQR. I went ahead and drew in PSR in red, although I had to I went over the red line here with the blue one because I drew TQR. That's this one here in blue. This line, it doesn't exactly match up. I drew it a little bit above the red line just to keep them separate. This one, I probably should have made the red line off to one side or a bit to show that this is also part of the red triangle. Well, for similarity, usually the easiest thing to do is try to find two angles that are congruent. If you get two congruent angles, you've got similarity. Well, for that we need to take advantage of the fact that we have inscribed angles. Inscribed angles which intercept the same arc are congruent. So we have QPS intercepts QS. On the other hand, QTS intercepts QS. So these two angles must be congruent. Can we spot another pair of congruent angles? Well, notice that this line here, pardon me, let's call it a segment, that's what it really is, SR, is part of PSR. On the other hand, it's part of TQR also, and the same thing over here. This angle right here, well, it's common to both triangles. In other words, it's congruent to itself. In this triangle, we could call it angle PRS. In the blue triangle, we would call it angle QRT. But you can see that they are both, this angle is part of both triangles. Naturally, it's congruent to itself. So, boom, we've got angle, angle, two angles that are congruent. So, these two are similar to each other. Pretty easy. And angle, angle, that's a good place to start when you're trying to show similarity. Especially when they haven't given you any side lengths. That's a good clue that you're going to have to find a couple of congruent angles because, well, there might be other ways to show that we have some similarity by using ratios of intersections. For instance, this section, we have a ratio of this, say, to this, and this to this. We might be able to fool around with some ratios and show similarity also, but angle, angle is the simplest way. Well, this one's not too bad. As you remember, the measure of an inscribed arc is double, pardon me, the measure of an inscribed angle is double the measure of the arc which it intercepts. And y would be, if we consider y as the measure of the intercepted arc, then it's just, we can write y equals 2x. minimum value for x is 0. The maximum would be 180. So we may have to change these numbers a bit. For instance, if each of these ticks were 45 degrees, yeah, let's see here, we got 45, 90, 135, 180, and that's about as far as x can go. X can't get any bigger than 180. Y can't get any bigger than 360. That's the Y up here. So, if we were to draw this, so this is pretty easy to graph. When x is 45, y is 90. When x is 90, y is 180. And on up to x can only go as far as 180, so it ends right up here off the graph. Oh well. And this up here, if I had room to continue, the vertical mark would be 360, and this would be 180. So the last point up here would be the point 180, 360. And down here, 0, 0 is still on the graph because 2 times 0 is still 0. So that works. Well, this one, they ask you to come up with statements about arcs and then segments. I believe I've looked at some answers that people came up with. They sometimes mention the arcs first, but everything you can say about the arcs depends on the chords, which are segments. So, in my opinion, you should write statements about the segments and chords first, because everything we know about the arcs just follows from what we know about the chords and the segments. In other words, let's take this here. Luckily, they tell us JD equals JH. That's this segment and this segment. This is the perpendicular distance from the point to the line. They're congruent, meaning each chord is equidistant from the center. And we know from, way back in the first or second section, they told us that chords which are equidistant from the center have to be congruent. That would be my starting point. We know that CA is congruent to EG. Gee whiz, there we go. What else do we know? Well, radius can always just be extended out the other side and be considered a diameter. What do we know about a diameter which intersects a chord perpendicularly? Well, we have a theorem that goes both ways. Number one, if the radius is perpendicular to the chord, it's a bisector. On the other hand, if the radius bisects the chord, it has to be perpendicular. So, we can instantly write that EH equals HG. So, for the segments inside the circle, you can write quite a bit, or quite a few things. As I said right off the bat, because of the equidistance from the center, you can write that CA is congruent to EJ. That's this chord here is congruent to this chord. Because it's a bisector, we can write EH is congruent to HG. And we can also write that CD is congruent to DA. On the other hand, we have two segments which are congruent to each other. If we cut those in half, the halves will also have to be congruent. That just follows from simple algebra. The congruence implies equality. We cut them each in half, we still have an equality, and then the equality implies congruence. So, if EG is congruent to CA, then half of EG is congruent to half of CD, which is why you can write this huge statement here. All these halves are all congruent to each other. And what about JB and JF? Well, they're both radii. So they, of course, have to be congruent also. So there's quite a few things you could write about the segments in here, and I think I summed it up. You can relate almost every segment to some other segment. In fact, it's not almost. Every single segment can be related to some other segment. Except maybe, I don't know about HF and BD. I would expect them to be congruent. And probably if we could probably prove it. We draw a little triangle and we connect BC here and EF here. I think we could prove it. But we don't have a theorem floating around that I can remember that says that the distance from here to here will have to be the same as the distance from here to here. I'm sure it's true, and I think it would be easy to prove. But that might be one thing we couldn't automatically say. We could prove it easy enough. But I don't believe we have a theorem that says the distance from the circumference to a congruent chord is going to be the same. However, in fact, we could prove it easier than that, couldn't we? After all, if JF is the same as JB and JD is the same as JH, well, JF is just, HF is just JF minus JH. Maybe I should write that down. Because it turns out we actually do have, I was wrong, we've got two other segments which we can also very easily show are congruent. It hardly even rates a proof. Because this is a radius and this is a radius, so what we have is that JF equals JH, and these are the lengths now, plus HF. Okay, but JB equals JD plus DB. Well, JH and JD are equal. So if we subtract one from the other, or just substitute, for instance, I could write JH in here. And in here I could just as easily write JF. Since these two are equal, since we know JF and JB are congruent, and they're also, this is the sum of these two segments, and JB is the sum of these two segments, we can set them equal. Now, we're given that JH and JD are congruent, which means their lengths are equal, so we can just subtract whatever that length is from each side and get that DB equals HF. So there's one more congruence that I missed. HF is congruent to BD. So it is true. Every single segment in this circle, the way it's drawn, relates to some other segment in that circle. This is very symmetric. Now for the arcs. Arcs, which correspond to congruent chords, then the arcs are congruent. So this arc subtends this chord, and the arc CBA subtends the chord CA. Then CBA has to be congruent to EFG. That's because the chords associated with them, the chords which connect the two endpoints of the arcs, if they're congruent, the arcs are congruent. So we know this is true. That's one statement we can write about the arcs. However, the same theorem which says that the diameter perpendicular to the chord will bisect the chord, there's an extra little addition in that theorem which says it also bisects the corresponding arc. So BC has to be congruent to BA. That's the arc BC and the arc. So we have AB is congruent to BC. Well, by exactly the same reasoning, we have that EF is congruent to FG, and in fact, this is half. These are each half. All four of these, BC, EF, FG, and AB, are all exactly half of two congruent arcs, which means they're all congruent to each other. So we have BC, AB, also EF. Pardon me, that's congruent. And FG. So you could write a whole bunch of different, if you just write them in pairs, you can write BC is congruent to EF, FG is congruent to AB. If you pick two at a time, you could write several different statements, a lot more than two. Are there any other arcs that would be congruent? Well, no, there's no reason to say that CA and AG are congruent. There's no way we could know that. And in fact, there's lots and lots of ways to draw these congruent chords where these outside arcs are definitely not congruent. But the arcs between here and here, the corresponds to the chords, we can say all kinds of stuff about them. And we just did. Now this problem is, the one thing that's kind of cool about this problem, it shows how many assumptions we make when studying the past. We tend to assume that people in the past thought the same way we do. We look at this section, and to us, it's definitely, no doubt about it, part of a plate. It certainly looks like a plate, and if we would say, oh, we just finished this off here. This is all just part of a broken part of a circle. Well, maybe. Suppose. I admit this looks more like a dog bone than a serving tray, but suppose this was part of a tray. You could have just had two rounded ends for decorative purposes. In fact, they may not have even protruded. May have gone like this. They could have done that. Or maybe they were just weird. Maybe their plate went like that, and then like that, and then like that, and then like that. How do you know? Well, we just tend to assume a certain regularity in people thousands of years ago. We probably wouldn't make a plate that looked like this over here. And most serving trays, we make them rectangular. But who knows what people did thousands of years ago. So before you do anything, as an archaeologist, you're obviously making big assumptions about how the people back then were looking at things and how they thought about things. And who knows if that's right or not. Well, so much for archaeology. Let's look at the mathematics of this situation. I'm going to draw the diagram. Let's see here. Okay, this is very sensible. It's a good way to approach the problem if we go ahead and assume that this is just part of a circle. And actually it could have been part of an oblong too, couldn't it? I'll stop talking about that stuff. For now, let's just say that it's part of a circular plate, and we're going to figure out what the diameter of that plate would have been. First off, we got to trace this thing. So, well, they suggest the best way to arrive at figuring out the diameter of this thing would be to start by drawing an outline of the piece that we have. That's roughly an outline of this outer part of the plate here. And then we draw two chords of this circle. Well, we don't know it's a circle yet, I guess. We're just going to pretend that it's a circle. And if it was a circle, what would the diameter be based on this little piece that we have? Well, remember, the perpendicular bisector of a chord is a diameter. So if we could bisect this chord, that line will pass through the center. That won't tell us where the center is, but this line would pass through the center. If we did the same thing over here, the diameter, which is perpendicular to this chord, will also pass through the center. Or to put another way, any perpendicular bisector of a chord is part of a diameter. Diameters have to pass through the center, so if we draw two diameters, the point where they intersect, I'd say that was a center, wouldn't you? So, now that we've got our chords, we naturally just have to eyeball. I think with the t-square and a ruler, you could actually find the midpoint and then make sure that you were drawing something perpendicular. Or you could use your compass. Remember that? And you set one point here and you draw an arc out here, set another point here, draw an arc out there. Do the same thing over here. The points where those arcs intercept, if you join them, that will produce a perpendicular line which goes straight through the midpoint of the segment. So you could use your compass, or if you're on site and need something bigger, you could use a ruler to get a pretty good idea of what the midpoint was, and then a t-square to make sure you were perpendicular. After all, I guess you just want an estimate anyway, so it's not like we're going to build a spaceship out of this thing and it has to be 0.0001 tolerance everywhere. So here's the center anyway. And what we did was just like triangulating. Remember way back when we studied triangles? We found that if we could figure out if we were somewhere, anywhere, and we had, say, a frequency that we could identify and knew the direction of it, so we're somewhere on this line, and then we find another frequency and figure out its line, and then we're right here where those two direct lines from us to the station broadcasting that frequency, and the point where they intersect, well, that's where we are, and that's called triangulation. And that's just what we did here. We just basically figure out a way to triangulate our center. Well, now that we have the center of the circle here, if we wanted to know we could compute the radius. That's the distance from the center to the circumference. That's no problem. Now, what does they say here? Describe a method could use to estimate the diameter of the actual plate. Well, I don't know if I would go so far as to give it a big name like method. It's kind of an obvious thing to do. The radius, we'll say it's r. Yeah, I guess I can try to draw it in. Almost a straight line. If that's r, well, the method, that's what you want to call it, would be to multiply r by 2. That seems, I don't know, it's like describing walking as, what method do you use when you walk? Well, I put one foot in front of the other. Okay, you want to call that a method, fine, but it just seems to me like it's just something you do. I always think of methods as something a little more complex than just multiplying by 2. It seems so ridiculously obvious. But anyway, I couldn't argue with them. I'm sure they're smarter than me. Maybe method is the right word. Anyway, if you want the diameter, it's easy to compute the radius once you've got the center, and you get to the center by drawing part of the circumference. After that, you just multiply this by 2 and you've got the diameter. There are other things we could do. For instance, if you had a protractor, once you've got the center, it might not work out so well. I was thinking maybe if you could measure the arc of this, but to do that you'd need to know the central angle, which would cause you to find the center. And in that case, you could probably measure this distance just as easily as you could measure the arc. Now this one is actually pretty easy if you remember your equation for a circle. They give us the center. So we can immediately write part of it. We can write x minus a minus 2 squared plus y minus 4 squared equals, well, they didn't give us a radius, so we'll just have to write that for now. But what is r? Well, they tell us that when they say 3 minus 8 lies on the circle, I'm sure they mean that it lies on the circumference of the circle. That's how we're dealing with circles. We're not really thinking of the interior of the circle as the part of a circle. Although if you were to cut a circle out of construction paper, you would probably consider the whole thing as part of the circle. That's not what they mean right here. They mean the circumference. So all we have to do, if P lies on the circumference and C is the center, well, by definition, the distance from C to P is the radius. So what is that? Let's just say, let's go from here to here. Like 3 minus a minus 2, that's delta x, squared, plus minus 8 minus 4 and that'll give us r squared. So what is this? So if we lay this out, do a little arithmetic, we should get that r squared equals 169. This looks suspiciously like 13 squared to me, but we'll check that later and see if it's of any use. Right now we've got that r squared equals 169. So now it's super easy. We've got r, we've got the coordinates for the center of the circle. By now you can write this equation down so fast, I think you could flip off the lights and have this equation written down before it even got dark. So let's write it. We got x plus 2 squared. Well, that's supposed to be a 2. There we go. Y minus 4 squared. And that equals 169. Okay. That's the first part. What about the line that contains radius CP? Well, we're going to have to find the slope, which is pretty easy because it goes from here to here. And then given one point on the line, we could use either one. We can find B and get ourselves an equation of the line using the slope-intercept form. Next well, as I said, first thing we had to do is find the slope. Using P and C for the slope of the line that connects them, we get, once again, it's delta y, the rise over the run, we could say. That's delta y over delta x, or minus 8 minus 4. That's the minus 8 minus 4. And minus 3 minus a minus 2. 3 minus a minus 2. So we get minus 12 over 5. That is the change in the y-coordinate over the change in the x-coordinate, or rise over run. There's lots of different ways to remember that. Well, that gives us the slope. So now we can write that y equals minus 12 over 5 times x plus b. Well, now we just have to find some point which satisfies this equation, plug in x and y, and then solve for b. We can use either one of these points. I'll use C. Probably make it more complicated. I have a habit of choosing the wrong one when I've got a 50-50 choice. Let's see what happens. We've got the y-coordinate is 4 equals minus 2 times minus 12. It's 24 over 5. plus b. Or and we do a little algebra. This would be the same as 20 over 5, right? Multiply the top and the bottom by 5 in order to get a common denominator here, and then subtract 24 over 5 from each. And we'd get 20 over 5 minus 24 over 5. That'll give us minus 4 over 5. So the equation for our line is y equals minus 12 over 5, x plus, well, that's not right. You could say plus or minus 5, but that looks a little more reasonable. Minus 12 fifths times x minus 4 over 5. So that is the equation of the line that contains CP. Now we want a line that is tangent at P. And that's going to be pretty easy. I think I'll just get rid of this stuff down here. So we've already got this. Give myself room to work. This is where we found the equation for the line. Well, the tangent is perpendicular to the radius. And that's what we just found here. From C to the center to a point on the circle, on the circumference of the circle, that is a radius. So if we find a line perpendicular to that, we'll have the slope of the tangent, and then we'll have to use our point P, which lies on both lines, to get the actual equation. When we get the slope, we'll have part of it. We'll have this part here. Then we'll have to solve for B. Pretty much the same thing we did in B, except this time we're going to find the slope by taking the negative reciprocal. Remember, if the slope was 2, the line perpendicular to that would have a slope of minus 1 over 2. This is minus 12 over 5, so right away we can write that for our tangent line, our equation is going to look like 5 over 12 times x plus b. So using the point 3 minus 8, we can write y minus 8 equals 5 twelfths times 3 plus b. We just plugged our known x and y coordinates for this line. Well, if we do this, notice we can cancel the 3 and make this 5 over 4, right? 3 goes into 12 4 times. So make this, just cross this out and make it a 4, and drop the 3, and then subtract 5 fourths from each side. Well, minus 8 is the same as minus 32 over 4, minus 5 over 4. That gives us that b is minus 37 over 4. Or, what is that actually? 9 and minus 9 and 1/4. Well, doesn't really matter. They didn't ask us to simplify anything, so I think it would be legitimate to just write y equals 5 twelfths b. Pardon me, it's not b. That would be an x, wouldn't it? Minus 37 over 4. This is the equation for our tangent at the point P. And again, it was really pretty easy. We just had to remember that for a perpendicular line, the slope is the negative reciprocal. Once you got that, you can write out this. You can pick a point on the line. In this case, we only know one point on the line. That's the point of tangency. Plug in y and x, solve for b, and you got the line. So this is all, used a lot of stuff that we knew even before we took a look at this section in the chapter, didn't we? Except maybe the equation for the circle. We weren't that good at that up until now. And of course, Now we are experts. Oh, and that's it for the review. The next chapter is going to be pretty much all very useful stuff. Measuring length and area. And that gets used all over the place. The Egyptians were doing that 5,000 years ago. And people have been doing it ever since. So, something that lasts for 5,000 years is probably worth learning something about. Yeah, that's about it.